So where we are in this big theory is currently we are at projective varieties, right? So we have shown these associations. So projective n space over an algebraically closed field K, small k. So you can look at projective varieties Y, you can look at closed sets, and you can look at a point. So the associations are that in the algebraic word, which is basically coming from the polynomial ring in n+1 variables. So x0 is the new variable. So x0, x1, x2, dot dot xn. So those are this basically will be the location from where the functions will come from. This is the most basic ring. So variety Y, actually I think I meant subset Y. So subset Y, you can apply the I functor and you can get an ideal of that subset. And on this side, if you started with a subset of polynomials T, then you can apply the Z functor and you can get the zeros of that. That's called a closed set. On this side, this ideal is a homogeneous ideal for the projective variety. And one-to-one correspondences are between closed subset Y's and radical homogeneous ideal. Okay, and then it becomes more and more precise. So for projective variety, you will have a homogeneous prime ideal. For a point, you will have a maximal homogeneous ideal. Is that clear? And the projective space we will study via affine varieties, via the affine space, because there is this natural thing, the proposition that projective n space has an open cover via n+1 many affine n spaces, which is just the obvious thing. You have n+1 coordinates a0, a1, dot dot an. You set a0 to be not 0 or a1 to be not 0 or a2 to be not 0 and so on. Those are the UIs. Okay, and then you can see the map. There is a map from UI to a to the n. And then you can do that for all the i's. So you actually get a cover, each of which is affine. Each part of it is affine. And the map is to the projective n space. So this is conceptually, it's a new object because it's very different from whatever you have seen before it. So it is not really, you cannot realize that space by any single affine variety. That actually you can take it as an exercise, that this is not an affine variety, but it's a union of affine varieties. And this property of projective n space just naturally extends to all quasi-projective varieties, because you can, if you have a general Y, then you just intersect Y with UI to get the affine variety. Any questions? Okay, so now we will compare varieties, because we now have so many types. We want a way to compare them, basically map one to the next, and we'll do it in more and more precise ways. So first thing we will start with is an analog from complex analysis or real analysis. So we want to study between affine varieties X and Y, which can also be projective. So So we need to be extra careful about continuity, preserving that. Basically, you have this Zariski topology on X and Y. So there is a notion of closed sets, open sets. You want to preserve them. Okay, so when that happens, we call the map continuous. So it's at this point, it is not clear what maps will preserve it. Okay, so we will make it precise and then give a definition. To preserve both the algebraic and geometric or topological properties. So algebraic property is that we want to stay close to the polynomial ring. Our functions should emerge from there. And geometric means that we should stay close, we should preserve the neighborhoods or the open neighborhood of a point. So this is kind of a diversion. So from topology or analysis, we call a map phi continuous if for every open subset of Y, so we are looking at the range, right? So there, any open neighborhood, what should happen with respect to phi? Look at the pre-image, that should be open. So phi inverse V is open in X. Okay, so you want this property. Every open in the pre-image should be open. Then we call a map continuous. Okay. Obviously, this is quite intuitive, and you can draw pictures when you are doing real analysis, which is you can do the following. So look at map from reals to reals, removing 0, so that I can send x to 1 by x, and you can show that this map is continuous in the real world because of this picture. So if you plot it, so this is the x-axis. So 1 by x close to 0 is very large, right? And then at infinity it is very small, so it's like this. And the other part is the negative side. So on negative it is in this quadrant. So we have the whole x-axis except the point 0. And you can see that if you pick any open set, like from here to here, right, you can see obviously that in the domain from here to here, it's continuous, right? So continuous intuitively means that when you draw it, you don't have to lift your pen. So you can see that in any part of this curve, the pre-image is continuous. So we deduce that this is continuous. And opposite example is if you looked at the whole real line, you sent x to 1 by x when it's defined, else you send it to 0. Right, so what will be the picture now? So now the same picture except that you will be forced to lift your pen because 0 here is also included, right? So the real line except 0 is the same picture, but at 0 you have included it. 0 comma 0 is there in the diagram, and you can see that what is the place where you have discontinuity in this map? At 0. So this is discontinuous around 0, right? Because if you try to draw the part around 0, then you have to lift it from 0 to infinity. So that is the thing you want to avoid. You don't want to study such functions, at least not in the beginning of the course. So we have to somehow avoid this in the definition when we give it algebraically. So intuitively, in a continuous map, you don't have jumps. So a small change in x leads to a small change in phi. Okay, this is the property geometrically we want, but we don't know how to define any of this over finite fields. So what we will do is that we'll just lift good things from actual analysis or geometry, which is polynomials and ratio of polynomials. Okay, and we'll call them forcefully continuous. And we'll show that it actually gels well with the definition of Zariski topology. So in that word, it is actually a continuous map. So we will study locally rational maps. So these are our best guide in this business. Rational functions. So basically, locally, the function should look like g over h, where g and h are polynomials. They are somehow special to achieve this property. So we'll not worry about the picture, we'll just then lift this bottom line that our maps should be rational functions, if not globally, at least on some neighborhood. So we are led to the following definition. For any quasi-affine variety, y, let's say in affine n space, subset of affine n space. So a function f from y to the base field k is regular at P P is a point on this quasi-affine variety if there exists some open neighborhood. So NBD will be the short form from the neighborhoods. If there is an open neighborhood of this point U such that f is equal to g by h on U. for some g and h in the coordinate ring of y. Okay, so remember the coordinate ring was essentially these polynomials which are defined on y. In the affine n space, full space, it's all the polynomials, otherwise it's polynomials modulo the ideal, defining ideal. So g and h should come from there. Okay, and their ratio is what is called also a rational function, but we will have a special meaning for that term here. So we are only calling this f a regular function which is regular at a point, given point P. With respect to some open neighborhood, it may not be true for all u's. It's true only for some u. And we call a function regular on the whole quasi AV. So f is regular on y. So we call it regular on y if it is regular for each point. Is that clear? So we just wanted g by h, but we define it point by point. And instead of just at a point, because a point is a closed subset, it's not really a neighborhood, so we actually pick a neighborhood around it. So there are the data here is a point, a neighborhood, and gh. And similar definition for quasi projective varieties. In the projective affine projective n space, except we need gh to be what?
Homogeneous of the same grade.
Right, so we need gh to be in the same grade, which is SD, homogeneous degree d polynomial for some d. Why is that? Why do you need, so g is in SD, but why do you need h also in SD? What happens if you take h to be s of d minus 1, degree d minus 1?
If you take g of t times that and divide by h of t times that, then t is not done.
Exactly. So in the space p to the n, the definition was that we only look at a point up to multiple. So if there is a degree difference between g and h, then you cannot make the definition correct. It won't be a function from these points up to this equivalence class or equivalence relation. Right. So 1 over x, for example, has no meaning because, or 1 over x0 has no meaning because x0 itself is not uniquely defined. X0 is defined only up to multiples. So you can't say 1 over x0, but you can say x1 over x0 because that's a unique thing. So in the projective line, if you look at x1 over x0, so obviously then we have to say x0 is not 0. If it is 0, then we can just choose or fix it to be 0. So this is certainly a map, but does it have all these properties which we want? So this is show that this is regular at 1 comma 0. Okay, so at 1 comma 0 its value is what? It will come from the first part because x0 is not 0, so its value will be 0. But more importantly, in the definition you have to pick an open neighborhood of the point u. It will be what? You can simply pick it to be the first open patch, which is this affine patch, x0 not equal to 0. Okay, just take that, take this u0 u0 contains this point, and you can see that on u0 f looks just like x1 over x0. Okay, so everything in that definition is satisfied, so it's a regular function at this point. What about the point 0 comma 1? So at 0 comma 1 the second definition will apply, so its value will be 0. So I mean it is well defined, but is it a regular function? Why not? How do you show this? So the problem is that you will not be able to find the open neighborhood U which contains 0 comma 1 and where you can express f as a fraction of two polynomials. Is that clear?
I assume 0 to be degree minus 100. S of minus.
Yeah.
But there can't even exist any polynomial also. 0 by 1 anything else.
Well, no, that is not the obstruction. No, you can also take, so constants are allowed, constants are valid functions.
And that's why constant will be degree 0, but 0 function.
Yeah, you can allow degree minus 1 also, that is not the problem. The problem is that there is no open neighborhood where the function is 0 everywhere. So whatever open neighborhood you will take of 0 comma 1, it will have something which is coming from the first part of the definition. So in some part it will be like x1 over x0, in some part it will be 0. So there is no common function. You cannot find a common g by h, that's the problem. So its definition is, I mean there is this discontinuity essentially, that in most of the part it is x1 by x0, whatever open patch you take, most part it is x1 over x0, and then there is just one position where it's 0. So you can't have a common g by h. So you can check this, it's easy to check. That's the obstruction in that. Let's look at 1 over x1 square plus 1 on the affine line. Let's say the real affine line. Yeah, so is this regular? Well, everywhere on the affine real line, this x1 square plus 1 will be non-zero, and it's also affine. So this is a regular function. But we prefer to see things on the affine complex line, right? What about that? So here there is a value x1 at which x1 square plus 1 will vanish, right? So it's not regular. Yeah, so the thing about this definition is that it's highly algebraic, so it is very sensitive to fields. But since we always will take an algebraically closed field, what you can learn from this example is that there should not be any denominator, because if there is a denominator h, then there will be some 0 in the algebraically closed field, and then it won't even be defined. So if you want a regular function throughout the space, then it has to be a polynomial. Is that clear? So functions regular on the whole affine space where k is k bar, k is algebraically closed. So these are exactly the polynomial ring, which is A, x1 to xn variables. Okay, so this is one simple fact from the definition. You should prove this if interested. Yeah, I think I remarked this before, that we have now many kinds of varieties. Affine, so AV, or quasi-AV, projective variety or quasi-PV. So these will just be referred as varieties now. Okay, we'll subdue the special type out of these 4 types, because usually, I mean, all the definitions and in the examples the context will be clear. In the definition, whatever we'll define will be the core thing. It can be simply, I mean, slightly changed if you want to go from affine to projective or projective to affine. So we'll just talk about variety now. Right, so regular functions we have defined, but we still have to give a way to compare 2 different varieties, right? The concept of morphism. So what should it satisfy?
So I have a question.
Yes.
You have shown that functions regular or ANK are only the polynomials present. It's possible like piecewise polynomials are there. That can also be regular.
That's right, but then using the Newton results you can prove that this won't happen.
No, so piecewise, sure.
That will never happen basically. The only regular functions will be the polynomial.
Okay, I see. You are saying that on different points, this g by h value, the g and h are changing according to the point. Yeah, maybe I think we can prove that in the next class. We'll use Hilbert's Nullstellensatz for that. So one of the key things in this proof, which I'm skipping for now, is that actually it can be done right here. So suppose you have a function which on an open patch u1 looks like g1 by h1, and on a different patch it looks like g2 by h2. Okay, so what I will show is that actually the gi's are equal and hi's are equal. So ultimately you can combine them into a single representation. Why is that? So this actually means that f on u1 intersection u2 is what? It's both, right? And now u1, since u1 and u2 were both open sets, their intersection is also open. Now open sets have the property that they are very large because our field is algebraically closed, right? So u1 intersection u2 again has infinitely many points. So you have these 4 polynomials such that g1 h2 is equal to g2 h1 over infinitely many, I mean over a open set. From that you can deduce that they are actually, so okay, let me explicitly say here that this is equalities on intersection. But from that you can deduce an absolute equality on y, on the whole variety y. So if you have an equality of fractions or rational functions on an open set, you can actually deduce it that they are equal. Almost in the polynomial ring you have this equality. So now you have a single g by h representation. And then this h will have some 0 somewhere, and that will be a contradiction. Okay. So what this, I mean, contradiction, or you can just deduce that, well, it's.
I think the trick will be that these denominators will together generate the whole polynomial.
g1 h1 is equal to g2 h2 on y, which will, okay, yeah, my space has reduced. So that's equal to some g by, we can just call it g by h, which will imply that actually h is a constant. When it is in reduced form, g by h has to be in the polynomial ring. That is what you will get. Okay, g by h then ultimately has to be a polynomial, because if it is not a polynomial, if there is a genuine h sitting there, then it has a 0. That's a contradiction. Yeah, so this is a very nice example of how these open sets, how the Zariski topology will give you everything you want pictorially also. Okay, but to actually prove it, you have to go through algebra, which most of the time I'll be skipping unless you interrupt me. Then you will see an algebraic proof.
But like this thing assumes that the intersection won't be null set.
No, these are open sets. So K is algebraically say K is a complex field. So open sets are way too big. So when you intersect two of them, it's again open.
No, it is open, but like it might be empty as well. Like, if like the points are far apart.
Yeah, but
You to a neighborhood of some point. So point P will belong there always.
it's another thing you have to prove, that it cannot be empty. It's actually very big.
So Zariski as a property.
Or we can say that the entire space cannot be broken into like a union of like you can say.
Yeah, it's also a variety. Yeah, exactly. It's a variety, so it's irreducible.
The open sets are dense. That's what.
Yeah.
They will always exist.
So, yeah, so the irreducibility is also important. It's a variety. Okay. So that is the proof sketch for the blue part. I hope now you appreciate regular functions better. So this is the point where we move to morphisms. So the thing that we want, so a good map phi between varieties which may be completely different. Okay, x and y are completely independent. We want to compare it through a map. So what should the map satisfy? Well, first of all, it should be continuous. So it should carry over the topological property well, which means that any open set V of y pre-image should be open in X. That is clear. You want that property. But you now also want the regular functions on top of X and the regular functions on top of Y. They should somehow be connected through Y. So it should take care of the following. Composition, let's say. So see, phi is taking x to y, the points, but if you look at a function, regular function say on y, that takes it to k, right? So in other words, there is a path to go from x to base field k. So what you want is that if g is a regular function, then this composed map should also be a regular function on x. So that is regular g on y should give you a regular g composed with phi on x. Okay, so this is a very important functor that you are now learning, that basically the geometry of x and y should be preserved under phi, but also this thing which sits above y, which is the ring of regular functions, under phi it should map to something good, to a subring of regular functions of x.
So here, this G is any regular function or some regular function?
No, it's any. Because, I mean, any G takes elements of y to k. So phi, I mean, if you want to define a good map phi to compare two varieties, then it should be true for all phi's and for all G's. Right, so these, I hope you appreciate that these two properties are very different. They are not quite related because the first property is only talking about subsets and the second property is only talking about regular function ring. Okay, so these two are needed together. One will not imply another second. So, okay, so with that philosophy, your definition is ready. How to compare two varieties. So for varieties xy, a morphism phi from x to y is a continuous map which is always in Zariski topology, right? Now we don't know any other topology in this course. Is a continuous map satisfying the following conditions. So for all open V, open sets V of y, for all regular functions G y to k, G composed with phi, which we call map F, which takes so G is regular on the whole of y, which means that it's also regular on V, and the pre-image of V is an open set. So let's look at that. Phi inverse V, arrow k. This is a regular function. On X. Is that clear? So morphism is just a map between two varieties which preserves all the data that you can think of. Okay, it preserves the topological information, it preserves regular functions and whatever is implied. Fine?
One clarification, when we say a variety, should both varieties same, like X should be affine and Y should be affine?
No, we don't assume anything. Yeah, because other things you have to deduce. So if I think you can map affine to projective and so on. Why not?
Always in projective varieties, there won't be any functions. There's nothing regular.
Yeah, you don't have to tell that. It's too soon to make those big claims. Okay. So this is also called a pullback. This thing that we did, this is called pullback of G. Right, because y is kind of forward, x is backward, and G was defined on y, so you are pulling it back to x and making it a function there. So this is the definition of pullback. And just a note that this thing is open in X. Right, so both the topological and the functional information is contained here in the definition of morphism. And second thing is for variety y, OY is the ring of regular functions. On Y. So I've already said that it's a ring, but you can also deduce that from the definition of regular functions, because it was defined to be, I mean, at a point we had picked the open neighborhood U, and there it was written as G by H, right? So if you have G1 by H1 and G2 by H2, then you can also add the two, right? So clearly addition, multiplication, all these things are defined, constants are there, because constants 0, 1 are treated as constant functions. They're also regular, at least on affine, affine or projective variety. So this is a ring, and we denote it by O of Y, this fancy O. Yeah, so if you are aware of the term sheaf, then this is the first example of sheaf. Okay, but you won't need that. But these are, so sheaf is the algebraic object which lives over the geometry. So we are defining the simplest kind of sheaf here. So what is O of affine line? Right, so regular functions on the line are, say, and since C is an algebraically closed field, in fact, it will be true for any algebraically closed field. So these are only the polynomials, right? And this is affine line, so one variate. So this is just Cx, which is the coordinate ring of the line. So A of that, right? And this property is true for any algebraically closed field small k. So second example is what Madhavan was saying. What do you think is the ring of regular functions of the projective line? What is this? So G by, you want these maps which at every point on the projective line should look like G by H. Now, I gave a proof sketch before that if they look in every open patch, they are like Gi by Hi, then there is a common G by H. From the common G by H, now you also recall that in the projective case, actually we had deduced in the affine case that G by H then will be a polynomial. In this case, what is the polynomial? Which is a ratio of 2 degree D homogeneous polynomials. Just a constant, right? So this is just the constant, which is all the complex numbers. So on the affine space, you get the coordinate ring. On the projective n space, you just get constants. Is that clear? Yeah, you may ask that if it is just, if O of y is just constants, then why have we defined it in such a complicated way and given it a name? The reason is that this O operator we can apply also on smaller things. So we can look at just a part of the projective line and look at O of that. That won't be constant. Okay, it's constant when you look at the global section. Locally, it will not be constant. So we'll see that as we develop this more. Yeah, maybe I should give an example, another example. Just to test you. So consider the following function. Okay, it's a map. It's defined on the projective line. So it is supposed to take the projective line to the base field, which in this case we are taking to be complex. So when x0 is not 0, then it is x1 over x0. When x1 is not 0, or in the case when x0 is 0, then it is x0 by x1. So we have defined this on these two open patches of the projective line. The question is this a regular function on P1C? Because it seems that anywhere you see, it is a ratio of two polynomials, right? That seems consistent with the definition of regular functions. Do you agree that this should also be in O of PC1, P1C? What? Do you agree with this? What is the problem in this?
Basically, on the intersection,
It behaves as x1 by
so the intersection will be a single element, which can never.
Right, yeah. So the test was in which you failed. So this is the definition of f on u0, and this is the definition of f on u1. So now, which was actually also in the proof sketch, that then for f to be a regular function, it should have a nice representation on this also, right? u0 intersection u1. So where both x0 and x1 are non-zero. So both the representations have to be equal. Now, which clearly is not the case, because you can just take x0 to be 1 and x1 to be 2. Right? So you are getting 2 by 1 is equal to 1 over 2. So which means that that's a contradiction. So what is being contradicted here is that this is not a regular function.
Yeah, it's not even well defined, this function.
Yeah, as a map, it is well defined. That's the thing. So I am just splitting hairs here. So there is a big difference between a map and a function and a regular function. These three things are different.
Take a point 1, 2. The first representation will be half, second will give me 2 by 1.
Yeah, but you can okay. Sorry.
This is not defined.
And then you have to give only one output, right, for an input. But then
Yeah, so it is, so what it is not is, it isn't even a function then. But I think it can still be called a map.
Like for multiple values for single input.
No, because you can say that I decompose my line into two parts, u0 and u1. And then I only look at these values. For u0, these are the value. Oh, but at the intersection there is a, yeah, okay, I see. So this is, yeah, the contradiction is that it's not a well-defined map. So f is ill-defined at u0 intersection u1. So in particular, it cannot be a function or a regular function. Yeah, so this is the content of that proof sketch I gave. You may think that by giving different g by h in different local patches, the definition will be satisfied, but then the problem will be that when you look at the intersection of these patches, the g by h will not match. Okay, so the definition of regular function is loaded with many invisible things that you don't see. It takes care of many issues. And that thing is now even more serious in morphism. Okay, so morphisms will be very special comparisons.
But here, if it was a function, then you see it would be regular. Or
Here it wasn't even a function, so everything.
Yeah, no, but the proof sketch already had these things, right? The proof sketch says that there has to be a common g by h, and then the h also has to be 1, essentially. Because if h is a genuine polynomial, then there will be roots. So, yeah, this, if you prove this, then I think you will understand all of this. Just prove that the regular functions on the projective line over an algebraically closed field is trivial. Only constants are there. That contains all these ideas. Okay, but yeah, but these are not, so these are not the only kind of functions. There are many others. Like in the general theory, we will be interested in functions which are not defined everywhere. They are defined only locally. So in one local neighborhood, or in one open neighborhood, the function is defined, in somewhere else it is not defined. So we also want to look at the set of locally defined functions, and that needs another definition. So there are many other functions outside OY. That are regular on some open patch U. Proper open patch U of Y. So basically getting this common G by H is a problem. It's too strict. So we'll now weaken it to only care about some open patch and not all, not everywhere. So now on, we'll use U comma F to denote a regular function F. So denote a function F that is regular on open U. So it's only defined there, nowhere else. Okay, so on an open patch only it is defined, and there it's a regular function, so it has this representation G by H. So to capture that data, we have to also put in the domain. So now instead of a function F on the whole variety Y, you should think of just U comma F. F with the domain. And there is an equivalence relation. So we define that equivalence relation as follows. So U comma F and V comma G will be treated as same, will be called same. So formally we'll call them related by this equivalence relation, tilde. If, what should happen? They should be equal on the intersection. Right, so U is a big open set, V is a big open set. They have some intersection which is also big. So if on this big common space F and G look the same, then we should call them the same. It could be a bit counterintuitive because we are ignoring what happens in U minus V and V minus U. Yeah, but somehow this will be good for theory. Okay, so we'll call F and G with their domains equal if on the intersection domain they are equal. Well, okay, so one intuition why the theory will still work very well is that we never care about a single neighborhood. we care about smaller and smaller neighborhoods. Okay, around a point, we only care about neighborhoods which are as close as possible to the point. So we always care about the intersection. We never care about bigger things. So with that intuition, it's enough for F and G. I mean, it's enough for us to call them equal if they are equal in a smaller space. We don't care about differences in the bigger space. And once you have this equivalence relation, you now have a brand new object which we call KY. So KY is the set of all the UFs such that U is open and regular F. And you mod out by the equivalence relation. Okay, so you look at all the functions essentially with their domain where they are defined, and with the understanding that there is a notion of equality amongst them. So this KY is called the function field of Y. Of the variety Y. Now if I'm calling it a field, then it should be a field, right? Do you see that it's a field? What is the inverse of U comma F? What is the inverse of F basically? Why should 1 over F be defined? So either F is 0, then we don't care. If F is non-zero, then 1 over F is defined at least somewhere in the word, right? Essentially in places where the zeros of F are absent. So complement of Z of F, which is an open set, right? So 1 over F is defined over some open set. There is some open domain. And since F had a representation G by H, the reciprocal has representation H by G on that open set. So it's of the same type. It's in the set. Okay, so, and then you can obviously see addition F1 plus F2, F1 multiplied by F2 and so on. So it was always a ring, but now it's also a field. The ring structure is coming from OY already. But the interesting thing that you now have because of the domain information is it's now a field. So this is called the function field of Y. And the elements of KY are called rational functions on Y. So these are the true rational functions. Okay, obviously it is inspired by functions of the type 1 over x or x1 over x0 or so on. Yeah, now it is something which is inherent in the given variety Y instead of coming from polynomials. Okay, so you have now regular functions on a variety, you have rational functions on a variety. And yeah, the first one is a ring, the second one is a field. And obviously OY is a subset, is a subring of KY. Is that clear? Okay. Yeah, so once we have this nice object, or maybe I give an example first. So for the affine line, what is KY? So you have to unpack that big definition with all these concepts. And in the end, you will get something very simple, which is Yeah, so first you look at OY. So OY we know is CX. And from that you can guess KY to be just change the bracket. Okay, so this is, so for example, new things that you have included are things like, well, 1 over x was not there, and you also have 1 over x square plus 1 and so on. So the reason why 1 over x square plus 1 was not there before was because there are zeros where the denominator vanishes, right? So that was not a thing which was regular on the whole of the affine line. But now you don't care about their vanishing because you will just exclude the vanishing part. The remaining is open. With the domain 1 over x is fine, right? So you can make this into a proof. You can show that ky is c of x. Yeah, the other example you don't even need to write down, but still let's test you. So what is k of y for the projective line? So OY was just constants. What should be ky? Will it again be constants? No, obviously not. No. So now, if you go through the proof, we looked at g by h, and we said that h will be 1, hence g will be 1. But now there is no need for h to be 1, right? So you can take now all the fractions. So g by h, where g and h are in SD. So these are basically the rational functions where, so this is, should write that. So g and h both are bivariates. So for example, x0 by x1 is there, and x0 square over x0 square plus x1 square is there, and so on. Okay, these bivariates equal degree, you can take that fraction. Is that fine? Yeah, so this is an interesting object, and now is the time to make it even more interesting. So what you can do now with this concept of equivalence of u comma f with v comma g, you can take a point, take a neighborhood and shrink it. Okay, so basically you get closer and closer to the point P, and so in the limiting case, what are the functions which remain? You want to study that. Okay, as you get closer and closer to the point P, what are the functions amongst ky which will live and others will be excluded? We want to understand that, and now remember, completely algebraically, right? There is no such picture. So you have to do this purely algebraically. So for a point P, let us look at functions. That are regular, arbitrarily small neighborhoods of P. Okay, that's the goal, and I'll give you the definition right away of this set of functions. So these are called the germs of, or germs on Y near P. So this is the set O sub py is the set of those functions which are defined at P, and well, basically P is contained in U. So P is contained in U, U is an open subset of Y, and F is regular. And then obviously you have this equivalence idea. So now if you only look at, so once you fix P, point P in Y, you only look at that part of Ky where P is covered by U. Okay, so that is called germs on Y near P. What this is defining geometrically is this functions which will remain defined at P no matter how small you get to P, and in the end actually becoming P. But you can never become P because P is a closed set, right? So open sets will always be slightly bigger or much bigger than P. So over all that you get the limit, right? But you get it now algebraically, so we don't really have a genuine notion of limit here like you had in real analysis. And the germs vanishing at P are somehow special. So these are functions that are defined at P, but when you evaluate them at P, you get the trivial thing which is 0. Okay, so these are the germs vanishing at P. It's the subset called MP of UF in OPY such that F at P is 0. Is that clear? Yeah, examples of this are actually trickier to write down. We'll do this explicitly next time, but let's attempt on the affine line over complex, and let's take the point P to be the 0 point. So what was O of Y? This was just Cx. Now can you unpack the definition to get OPY? What is this? And actually Ky also you know. So amongst all the rational functions in one variable over complex, which ones are defined around 0 in smaller and smaller neighborhoods trapping 0? You have to unpack this definition and do it in algebra.
I think F by G where G of P is not 0. That's it.
Yes. Well, G of P is 0 only when G is a multiple of X. Right? So this is basically all the functions G by H. So G is a arbitrary polynomial, and H, well, H is also a polynomial, but X doesn't divide H. Okay, so 1 by X is absent, but 1 over 1 minus X is fine, or 1 over X plus 1 is fine. Okay. Yeah, so we will define it in the next class. Obviously, why this affine line was a simple case, but I hope it shows you the algebraic trick which is happening. We'll formalize it via localization of a ring next time. Okay, so in general, we can write this we can unpack this definition in algebra and we can just say that this is some localization of the coordinate ring. And where localization means that you are allowed to divide polynomial g by certain polynomials, not all. In particular, in this case, you are allowed to divide by an h which is not a multiple of x. Okay, so these are the germs on the affine line near the point 0. And the germs which vanish, what's an example? So these will just be g's which are multiple. X should be a factor of g, right? So xg by h, that kind of. So x is there and x over 1 minus x is there and so on. So these are the germs. What you can show immediately is that MP is a ring. You can add two vanishing germs and you can multiply because you will still get functions defined at P and vanishing at P. More importantly, it's an ideal of what? Of OPY. Right, because functions which are defined in arbitrary small neighborhoods of P, those functions when you multiply with a function inside MP, then it becomes an element of MP. So that also you can show as an exercise. It's an ideal. And we'll prove actually more properties of OPY the next class. Some of these you can already try as an exercise. There are tons of properties of this object. So OPY is a K algebra. With MP as an ideal. I already mentioned that. More interestingly, OPY mod MP is a field. Okay, so in particular or equivalently, MP is a maximal ideal. And third is that not only MP a maximal ideal, there is no other maximal ideal present. It's a unique maximal ideal. So rings which have a unique maximal ideal are called, do you know the name? These are called local rings. And the name local ring already comes from this picture that we drew, right? Because these are rings which actually sit locally around a point on some variety. So such rings are called local rings. Where such is basically referring to the fact that your ring, let's say R, has a unique maximal ideal. So such rings are called local rings. They are used everywhere in commutative algebra. but geometrically they have this origin. That's where the name comes from. Okay, so you can try this. The proofs are simple. Just have to unpack the definition.